presentation today is tracing the boundaries of governmental decision, computational techniques of classification, and the global human settlement layer. So my research concerns the relationship between techniques of visibility and the rationalities and practices of decision-making in planning and governance. The question I ask is the following: how has this relationship been transformed by the advent of the digital? By visibility, I do not just refer to the sensorial and cognitive faculty of vision, as it has traditionally been attributed to animals, humans, and more recently to machines. Following Michel Foucault, I use the term visibility to indicate the diverse range of non-discursive practices which, in each epoch, determine the spatial conditions of possibility of what can be scientifically or even just reasonably said, and what can be acted upon or governed. My assumption is that technologies of visibility do not only determine what we see, but they also define what we act upon and how we take decisions about it. In this sense, visibility can be seen as an integral component or moment of governmental and planning processes. To govern a territory or plan the transformation of an environment, it is first necessary to establish a perceptual, that is, visual in a broad sense, connection with it. The techniques and tools whereby such connections are created are at once informed by contingent planning priorities and determining them. Using the framework outlined by Foucault in his 1963 book, The Birth of the Clinic, I claim that in the past decades, the proliferation of digital technologies of inscription and the boost of technologies of computation have radically transformed previous modes of specialization of the visible. On the one hand, what Foucault defined as the mode of perception or localization, that is the locus or perceptual field where phenomena gain visibility by virtue of their spatial distribution, shifted from physical space to the abstract mathematical space of digital information. On the other hand, and because of that, new computational operators took over what Foucault defined as the mode of configuration of the visible, the complex of spatial logics or semantic rules, whereby objects are perceived, talked about, and governed as separate from other objects and from the context surrounding them. So how did such transformation impact rationalities and practices of planning and governance? To answer to this question, I focus on a particular operation of configuration, which in my opinion plays a crucial role in the space of perception or localization of digital information. The identification or construction, the definition of continuous boundaries in operative space. I use the term targeting to define the visual pragmatic diagram articulated by this operation. I interpret targeting as the mode of visibility of decision. This is reflected by the very etymology of the word decision, from the Latin decidere, meaning to cut off, which evokes the indisputable spatial demarcation produced by continuous boundaries. Targets' boundaries can be arranged in different spatial configurations, each one of which corresponds to a different articulation of visual and pragmatic priorities. In my research, I focus on classification as a specific form of targeting. In classification, the entire operative space is divided into mutually exclusive areas or regions. Borrowing from Anne-Marie Moll and John Low's description of regional topology, in this type of targeting, I quote, each place is located at one side of a boundary, unquote, and therefore it belongs either to one or another region. Regions are defined following a principle of maximization of internal similarities, whereby, I quote, what is similar is close and what is different is elsewhere. Classificatory targeting is adopted whenever there is a need to assign different entities or different quantities of the same entity, typically money or ammunitions, to different regions, based on criteria of affinity, complementarity, or prioritization. In this respect, the visual spatial articulation of classification corresponds to the pragmatic mode of distribution or allocation. In the space of perception or localization of digital information, classificatory targeting is performed through a wide range of computational operations, both unsupervised, as in the case of clustering, and supervised, as in the case of machine learning. Because digital technologies of inscription work by translating any type of information onto a unique plane of equivalence made exclusively of sequences of ones and zeros, such operations are applied indiscriminately to the most diverse scales and to geographical, photographic, or abstract information. However, each one of such operations presents a distinct spatial functioning, which at once articulates and is informed by specific pragmatic priorities. To show how this visual spatial pragmatic nexus work, today I will focus on a particular technology of classification, operating at the scale of the planet, the global human settlement layer. The GHSL is a technology for the detection and classification of human presence on the surface of the Earth over a period spanning from 1975 to 2018. It was developed over the past 10 years at the Joint Research Center, which is one of the Director General of the European Commission. The core mandate of the Joint Research Center is to provide research, advice, and most importantly, scientific evidence for the European Commission policymaking work. Now, the term evidence, which comes from the Latin videre, to see, has the peculiarity of articulating a form of visibility obtained through empirical corroboration, utilized both in scientific and legal forums. The Global Human Settlement Layer is one of the most prominent projects in the context of the Joint Research Center's work on Earth observation. In its most recent iteration, the GHSL processes three different types of information: remotely sensed multispectral imagery from satellite collections across several years, spanning from 1975 to 2018, statistical population estimates for the same years, and crowdsourced voluntary geographic information. The main output of the GHSL equally consists of three products. The first is a continuous built-up area grid map, showing the proportion of built-up footprint area for each 30 meter by 30 meter cell. Here, built-up areas stand for buildings, and buildings are considered the best indicator of human presence. The second product is a population grid at a resolution of 2000 meter and 1 kilometer, derived from the combination of national census information and built-up area information. The third product is a settlement model layer at a resolution of 1 kilometer, which classifies settlement in three typologies: urban centers or cities, urban clusters or towns and semi-dense areas, and rural areas, with reference to the criteria established by the Eurostat's degree of urbanization protocol. It does so by clustering built-up and population grid cells in relation to population size, population density, and contiguity. The built-up and population grid are used to calculate exposure and trigger alert in relation to man-made and natural risk factors and to support decision in emergency and risk management. The population grid and settlement model layer are primarily used to monitor global patterns of urbanization and their carbon footprint across the planet, and to coordinate transnational policies, such as the ones presiding over the allocation of development funds and global aid. The global human settlement layer confronts a series of theoretical and practical problems common to computational technologies of visibility designed to support decision-making at the scale of the whole planet. However, the way in which the GHSL responds to these problems is very different from previous and coeval technologies for the classification of human presence on Earth. As I will try to show, This difference reflects the specific pragmatic priorities the GHSL is designed to serve. In turn, the computational classificatory techniques which implement those priorities bear the mark of the situated operative context in which the GHSL was developed. The first problem concerns how to bridge the semantic and visual gap between remotely sensed information, which only registers different degrees of reflection of electromagnetic radiations bounced by objects on the surface of the Earth, and the abstract and complexly defined classes devised to support decision-making. This does not only entail finding the most efficient way to attribute each point of the information space to one of a series of predetermined target classes. It also entails establishing effective criteria to define those classes in such a way as to overcome practical limits and meet the pragmatic priorities of each specific operative context. The second problem concerns the sheer amount, that is the big scale, of Earth observation data. This aspect, added to the data's rapidly changing nature, to its incompleteness, lack of harmonization, and inconsistency, makes it very hard to perform classification of remotely sensed data with a high level of resolution and reliability. Traditionally, these problems have been approached in two alternative ways. The first relies primarily on human intelligence and expertise to produce causal models capable of attributing input data to semantically complex target classes. On top of being very expensive and requiring a lot of expert time, this method is only reliable when input data is very stable. This can only happen when the extent of operative space to be classified is very limited. For this reason, this method is unsuitable to the task faced by the GHSL, which is to classify the entire surface of the Earth. The second method relies on complex machine learning procedures, such as support vector machines, neural networks, etc., which entrust artificial intelligence with the task of formulating inferential models linking sensed data to the highly abstract classes provided by human trainers. On top of being extremely computationally intensive and expensive, this method is unsuitable to classificatory tasks characterized by vast and inconsistent data sets and large and highly impure training sets. The global human settlement layer adopts a very different approach. Firstly, instead of working with highly abstract and semantically complex classes from the outset, the GHSL operates through a stepwise process of stratification of down-to-earth, that is low-level semantics, classificatory criteria. Secondly, rather than relying on highly sophisticated and computationally expensive classificatory technologies, the GHSL adopts a much more robust and economic method called symbolic machine learning. This method works in two phases. The first phase, input data relative to electromagnetic refraction, is discretized. That is, it is transformed into sequences of discrete symbols. In the second phase, these sequences are classified by searching for associations with large crowdsourced voluntary geographic information databases, which are used as readily available classified training sets, covering the whole extent of the space to be classified, that is, the whole surface of the Earth, albeit with a lower resolution. By using statistically assessed associations as a proxy for identity, this method embraces a data-driven inductive inferential approach, rather than one based on the production of causal deterministic models. It does so by employing elementary statistical techniques, similar to the ones utilized in actuarial tables since the beginning of statistics, in customer segmentation techniques, or more recently in techniques for genetic association. One of the main virtues of such techniques is their tolerance to error in the learning set, which in the GHSL is as high as 49%. Such feature makes them extremely efficient in a context characterized by highly unreliable, noisy, and heterogeneous training sets. The stepwise semantic approach and the symbolic machine learning technique adopted by in the GHSL are instrumental to creating a classificatory tool which privileges robustness and transparency over accuracy. Its computationally straightforwardness and insistence on low-level semantics bears the imprint of the operative context in which it was originally developed, that of global crisis management operations in war-torn zones. In fact, crisis contexts are characterized not only by highly competitive and divergent priorities, but also by difficulty to find agreement on the very terms of the discussion. For this reason, the GHSL is conceived more as a tool for problem setting than problem solving. It is a proactive tool designed to visually set the terms of the discussion. On the other hand, in its attempt to create a standardized classificatory technology of visibility, which encompasses the whole surface of the Earth, the GHSL articulates the pragmatic priorities of the post-2015 international policy framework, which comprises the 2016 UN Third Habitat Conference, the 2030 Agenda on Sustainable Development Goals, the UN Framework Convention on Climate Change, and the Sendai Framework for Disaster Risk Reduction. In conclusion, the GHSL responds to problematics associated to the construction of a classificatory tool for visibility operating at the scale of the planet. If the etymological meaning of the word crisis is the moment of decision, the scale and spatial logic of the GHSL's decisional boundaries reflect the current political scenario in which the horizon of crisis increasingly reaches a global scale, demanding for global coordinated methods of visibility and governance. That's it. Thank you.